All right, so I wanted to finish our discussion of just kind of setting up how we want to think about uniform circular motion. Reviewing back to the definition, so an object is in uniform circular motion if it moves with constant speed in a circular path. So again, if you think about an object swinging on a string, for example, at a steady speed, that's a good example of uniform circular motion. So we talked about, if it's moving in this circular path, at any given instant, the velocity vector, it's traveling that path of that little piece of the circle. So the ball's velocity vector points tangent to the circle. So it points tangent to the circle that it's moving in. Now, this is considered acceleration, so I'm going to say yes. And the reason why is the physics definition of acceleration is any change in velocity. So the magnitude of the velocity does not change. The speed does not change. But because the direction is changing, this is technically acceleration. And the acceleration vector always points towards the middle of the circular path. So if we look at this instant, for example, this acceleration vector is not going to speed up or slow down the velocity, but it is going to change the direction. And when it moves a little bit further, the velocity vector is still tangent to the circle, and the acceleration vector is pointing towards the center. So the answer to this question, what direction does the acceleration vector point, is to the center of the circular path. So what we know about acceleration is caused by an unbalanced force. So we must have an unbalanced force in the direction of the acceleration. So the net force on this object to produce this circular motion also must point towards the center of the circular path. Now, to kind of prove that point, when you swing a ball around on a string, what's providing that inward pointing force is the string itself. The string stretches and provides a tension force pointing towards the inside of the circle. Now, if all of a sudden you were to stop providing that force, maybe the string breaks, or you just cut the string, or you let go of the string, the net force pointing inward is going to go away. It's not going to cause an acceleration anymore, and the object is just going to fly off tangent to the circle. So if you were to look from above and the string broke as it came to this point, the object would just start going in a straight line because there is no unbalanced force on it anymore. So what would happen if the net force on the ball were suddenly reduced to zero? The ball would move in a straight line at steady speed, at least as viewed from the top. It would accelerate downward due to gravity, but we're kind of just ignoring that viewpoint. So from top view, it would just move off in a straight line depending on where the force was taken away. So some terminology that we'll use for uniform circular motion: the name of that net force that accelerates an object towards the center of a circular path is called a centripetal force. So that is spelled like this: centripetal. Centripetal means center seeking. Don't confuse that with centrifugal. Some people talk about centrifugal force. That's actually spelled like this. And centrifugal force means center fleeing. Centrifugal force is that sensation that we're kind of thrown outwards when we're moving in a circular path. It's not actually a force, it's just your inertia, which would tend to carry you in a straight line. So centrifugal force is sometimes called an imaginary force or a perceived force. But if you step out of kind of the viewpoint of the object and watch it, say from above, there is no outward pointing force. There's just inertia that carries the object in a straight line. And that's something we can talk more about moving forward. So along with this center-seeking net force, we also have what it produces is a centripetal acceleration. So there are three things that you can do to an object in circular motion that would require you to have more force to keep it, more unbalanced force, centripetal force to keep it on a circular path. And the short video clip that hopefully you've watched or maybe we've discussed in class highlights those three things. So the first thing that you can change is the speed. So if you swing something faster, or if it's moving faster, you actually need more force to keep it in that circular path. So the speed or the magnitude of the velocity is one thing we're going to look at. The mass of the object itself is going to influence how much net force you need. If you're trying to swing around a bowling ball compared to a tennis ball, the bowling ball has more mass. You're going to need more center-seeking force to keep it on a circular path. And then the last thing that will influence it is the size of the circle or its radius. Big circles have a gentler curve. They don't require as much center-seeking unbalanced force as a tight circle. To keep something moving in a tight circle, you're going to need more net force. So on the back of this handout, there's a number of steps to go through to prove some equations for both centripetal acceleration and centripetal force. There's an associated video to watch if I'm not there to present it in class. Thank you for watching.